Alrighty, so find leaves of a binary tree. The next question. And let's kind of dive right into it. Yeah, let's get right into it. So what do? Yeah, let's do it this way. Actually, oh, yeah, hold on. Kind of, there we go. All right. Find leaves of a binary tree. All right, let's give it a shot. It's got high acceptance, so this should be relatively quick. I don't have too much time. We have a few more minutes, but maybe we do a couple more problems in one of these and maybe another one. This one I think will be kind of quick. Collect the tree's nodes as if you were doing this. Collect and remove all leaves. Repeat until the tree is empty. Oh, no kidding. All the leaves. Ah, into sections. Okay, that's kind of interesting. Huh. Moving them. All considered correct. Per level, it doesn't matter the order. Okay, interesting. All right. Hopefully this isn't too difficult. I don't know what to expect here with this question. It's kind of like a... I don't know if you should actually remove the leaves as if you were doing this. Should we damage the tree? I mean, we technically could remove each leaf. So one approach would be to... There are like a few different ideas that I have. One approach would be to literally find the leaves, like a routine that just like get leaves, and then actually and also remove those leaves. Get and remove leaves routine, and just run that iteratively until the tree is empty. That would be kind of expensive though. I think that would be, in terms of time, I think it's computationally like quadratic time. So I don't think I want to do that because I mean, also, how's my voice? Should I need to be louder, lower? I think maybe, yeah, it's okay. It's kind of, I'm talking kind of loudly. So we could do that. I mean, that's not good though. We don't want to do that. However, technically you can. Probably. I'm thinking a breadth first search solution is probably pretty good. You could also you can do this backwards also and say you can create like a depth tree, something like that. No, can you do that? No, the node's at the same depth. Yeah, no, no, not quite. Not quite. It actually would be the depth of that subtree. The largest, yeah, the depth of that subtree. So this subtree, the depth is 2. This subtree, the depth is 1. This subtree, the depth is 3. 1, 2, 3, right? So this is its own, it's 3, this is 2, and these are 1, right? So the depth for each subtree, you could, we'll just write a simple recursion here and we'll sort of return information as we go. You want the maximum of the depth for a particular node, you're going to take the maximum of the depth of the left subtree and the right subtree plus 1. And I'm going to create a vector. You could do a hash map. Hash map's fine. Do we want to find the max depth first and then find the yeah, it doesn't matter if you create a hash map first. I think the max depth and then you can do it all in one shot. So we have this. We'll create an unordered map, or even do a. Sorry, excuse me. No. You can use a vector. That's fine. No, that works. The vector's fine. So we get the max depth for each node. Push it into the vector if the vector's not big enough. Push the value at that depth. Do it recursively. Yeah, I think you can do this. I think it's actually, hold on. I think it's not bad at all. Let me see something here. A vector of vectors of ints. We're going to say ret. We're going to say excuse me. Auto recurse is going to be, yeah, this could be done. Root recurse. Tree node R, auto F. Okay. So what we're going to look to do, and I think we also want to return the depth itself. Yeah, the return value is good. I think that was what I was learning before, is it's a little bit easier to actually return. So base case, we say if not R, return 0, right? And we say int left is f of R left. That's it. And right is f of R right. Oh, no, sorry, it's not it. You have one extra detail here. Left, right, return standard max of left, right, plus 1. Right, you do that, and you say, no, you say int depth, and now you're going to say if depth is greater than ret.size, or equal to, then you're going to say ret.pushback, a new vector of ints with one int in it, and it's going to be the depth. Otherwise, ret depth dot pushback depth, return that depth. So we're going to update our vector as we move through. What does this do? Does this give us what we want? Wrong. 1, 1, 1, 2, 2. Oh. Ah. It's not the depth, it's the value. That's my mistake. Let's give that a shot. Wrong answer. 4, 5, 3, 2, 1. Ooh. Really? That can't be right. Oh, you know why? It's depth of 0. Size is 0, depth is 0. I think, well, that's fine. This is depth of 1. 2, 3. Or should these be 0, 1, 2? I think 0, 1, 2 is probably better. No, it shouldn't matter. They're just gonna be. There's just gonna be. Well, let's do 1. Yeah, I mean, let's do -1 even. Could even try that. See what happens here. Oh, there you go. Okay, it had something to do with it. I don't know what it was, but yeah. All right, test cases. Okay, let's think about this here. Degenerate test case. Let's be a little more disciplined here. How are we doing? 10 minutes. Okay. All right, degenerate test case. Now let's do instead of 1, 2, 3, 4, 5. Let's do the other way. Let's do 1. Let's do some testing so we have this right. Oh, it's time for me to go. It's time for me to get up out of here. Skedaddle. Time for me to skedaddle. All right, let's do 1, 2, 2. We want this to be null. Null, null. And 3. Well, okay, 3. Excuse me. And 2 is going to be null. So if you do the child, so multiply by 2, so 0, 1, multiply by 2 gives you 0, 1, 2. 0, 1, 2, this is one child. This is the other child. We actually want both of these to be null. And then this is the left child. The right child should be 3 of, no, this is right. This should be, why did I get 2? That's so confusing. This was index 1, then multiply by 2, 0, 1, 2. And then add 0 as the left child, add 1 as the right child. The children of 2, but now why is, oh, there's another 3 in there, that's why it's confusing, okay. And we want to put, what does this give us? I'm going to put 4, so this is index 1 multiplied by 2 and is, or this is index 2 multiplied by 2, we get 4. 0, 1, 2, 3, 4. I also want this to be empty. There's another 3 somewhere in here also. No, there's not. 1, 2, 3, 4, 5. Yeah, okay. That's what we want. Alright, I want to try this test case. I can get rid of the visualizer as well. Okay. Yeah, that's convincing. I kind of want to just try some random input too. See how that goes. I don't know. It's kind of hard because you have random input. It's like it could work, but you don't know why it would fail. Let's not be cocky here, overconfident here. Invalid test case. Oh. Alright, let's go for it. I don't know. I don't know, man. I don't know. It feels like maybe I'm missing something somewhere. I don't really know why this works too either. I don't entirely know. Let's go for it. Hey, 100%. Not bad. Not too shabby. Too shabby shabs. Probably not as efficient as it could be. Well, pretty, not too bad. Not too bad. Let's, oh, I don't need to go right now, immediately. Like I have, that was pretty good, 14 minutes. Not too bad. I don't need to go immediately. I have like a few minutes, but you know, I should go because it's better to be early than to be late. And I'm often late. Like when you're early, you could just hang around and then you're on time. But if you're late, you're just late. So let me go. I'm gonna go. I'm actually gonna go meet with the church group, the church that I attend. So yeah, that should be interesting. I'm glad to do that. Grateful to do that. So glad, so happy, so grateful. Praise God, man. Praise God for all the things that He gives us. And yeah, so let me go. Thank you all for watching. Today was super short, but at least we did something, And yeah, I appreciate you, watching. And I will talk to you soon. Have a good rest of your day. Take care.